Pendulums. We see them everywhere. In very old clocks, in parks, and in amusement park rides. So what's a pendulum? A pendulum is a device made of a weight suspended from a pivot so that it can swing freely. When it is displaced sideways from its resting, which is what we call the equilibrium position, the gravity will then impose a restoring force on the pendulum and accelerate it back towards its equilibrium position. This causes the pendulum to swing back and forth around the equilibrium position. Then what's a double pendulum? Double pendulum, also known as a chaotic pendulum, is a pendulum with another pendulum attached to its end. Now I will do 3 trials of observation with my very primitive double pendulum, which I made with cardboard and a cloth hanger. Each trial starts from roughly the same set of initial conditions, which means that they have the same lengths, same mass, same angles, and also the same initial velocities. In each trial, the movements of the double pendulum has been different and unpredictable, even though I've tried my best to start the double pendulum from the same height and the same angle for each trial. Does that mean the motion of the double pendulum is completely random? Note that a random system is a system that could produce different outcomes from the same sets of initial conditions. I made a Python simulation of 3 double pendulums starting at the same time. They all have the same initial conditions. That means that they share the same lengths, same initial angles, and the same mass. I also let their initial velocities to all be zeros. I would then release them at the same time. That means they all initially overlap with each other. What do we predict will happen then? Although initially the differences between the movements of the 3 double pendulums were unnoticeable, we soon could see that the very small difference in their starting angles made their later movements completely different. This is the same phenomenon we saw earlier in my cardboard double pendulum. It was impossible for me to ensure that they actually all have the exact same starting conditions, unlike in my first Python simulations. In real life, it's not really possible for anyone using any sort of materials, even if they're not using cardboards, to make sure that their double pendulum always start at the same initial conditions. This is only possible in simulations. But what this tells us is that the double pendulum is a chaotic system instead of a random system. This means that any small changes in the starting conditions could have a huge influence on the subsequent movements and behaviors. An example of the chaotic system would be the butterfly effect. The path of a tornado could be influenced by a distant butterfly flapping its wings several weeks earlier.